Thank you, Khalil. Thank you, Ismail, and thank you, the organizing committee. So I am very happy to be here. So I tried to show what we are doing in lithium-ion and also next generation on solid-state batteries. Of course, this is open innovation work. It's a collaboration with CNRS and my friend Michel Armand from CIC Spain, and also long-term relationship with Professor John Goodenough. So first, I'd like to congratulations of my friend and my co-worker John Goodenough. He got a Nobel Prize, and I am be honored that the Nobel Prize committee, they invite me to be with him on 10 December. So, but this is good news also for battery communities. Other thing also, Hydro-Quebec was supporting John for over 30 years. So we're supporting his work, nominations. And this is one of the best award that John, he get Fermi Award. Chicago people are here. So we have John Goodenough here, myself, and this guy, very important guy. He was, even his Nobel Prize in Physics. Stephen Chu, was Minister of Energy at Department of Energy, of course, Department of Energy, US, under Obama. And this guy was supporting also the batteries for material science to also manufacturing, and not only supporting US, but supporting also North American. And Hydro-Quebec also was part of many programs from DOE like USABC and so on. If you go to Hydro-Quebec, almost 90.8% are for hydro green. And you can see in the case of today, only Hydro-Quebec as utility company, they have their center of research since 1967. So you can see we have 63 hydropower plants, 258,000 kilometers as transportations, and we have only 4.3 millions of clients. So Hydro-Quebec build, generate, transport, and distribute. You can see 2,005 terawatt-hour of production. Just if you compare, in Morocco is 30 terawatt-hours. It's a huge excess of powers. So we generate about 13 billion a year, and the total income, because the company is 100% belong to the state company, state-owned government. So we give around 4 billion as income to the government, what the government will be invest in healthcare and educations. We have the cheapest electricity, sure, 100% in North America and maybe in the world. So if we compare Montreal here, using 1,000 kilowatt hours, we just pay $71. If you are in New York here, you pay $287. Also because our energy is clean, you can see here that generation of greenhouse emissions, we are less than 3%, Canada about 12%, USA 28%, and in the world 30%. So when you go for research and development, Hydro-Quebec start working on lithium battery in 1967 non-stop. So the research center of excellence today, we are around 120 scientific. Of course, we have a big, large portfolio patented, and we license over 60 licenses worldwide. And just from 2011, the income mainly for license were 220 millions, very successful. That's what Khalil, he said about iron phosphate. And the publication also, we are balancing between fundamental science and also applications. This is very interesting because I like the history. I try to summarize the history from Mesopotamia. So we can see the first battery was Mesopotamia using the same anode and cathode as Volta. And then we can see Volta here, what we are today, we're using Volt. And then we come with lead acid batteries, nickel metal hydride. But not forget, you can see at least Hydro-Quebec was making two interesting breakthroughs. In 1997-9, we come with the first solid-state batteries. And what Khalil said, of course, with the help of John Goodenough, in 1995, we come with lithium-ion based on iron phosphate, with graphite and LTU, and we're showing for first time fast charge in 1 minute. With LTU, we show this is in next. And we focus, we believe that the next years, the behind lithium ion will be appear and will be focusing only in solid state battery as Hydro-Quebec. It can be lithium air, it can be lithium sulfur, but we are sure that beyond lithium ion will be appear. So this is just for the history, and you can see, at least in 1978, Hydro-Quebec and CNRS, they patented the concept of lithium polymer battery, solid state battery, and also rocking chair battery. You can see at this time we call it rocking chair because the state of lithium inside anode, cathode, and electrolyte is ionic. And then you can see for the solid battery here, so we can see the concept was patented in the same year. So we have the lithium as negative electrodes, solid electrolyte, and cathode material. And this is in 1979. So in the solid state, we were starting in 1979, thanks to USEBC and Department of Energy, and this at this time was consortium between 3M and Argonne National Hydro-Quebec. We licensed this technology Gen 1 to Bolloré Group, and they will show during this presentation that Gen 1 is in use at electric vehicles and also for energy storage and buses. And now we are coming with Gen 2 and Gen 3, so we can explain a little bit during my presentation. The concept that we use in Hydro-Quebec, this what my title is from atoms to the system and recycling, and we call it, this is a green circular economy. So usually we go from genome materials as DFT for over 25 years. We create new materials. We synthesize materials, and then we scale the materials to 30 tons. We make coin cells, flat cells, and also modules packs in the same place, and then we recycle. Other thing also, as I said, we are open innovation. We are supporting also universities and also giving licenses. You can see many of our licenses are worldwide, in USA, in Japan. Many in Japan, we have over 40 licenses in Japan using our technology and so on. You have Taiwan, you have in Brazil, and other in France, and so on. Okay, so I divide my talk in two applications: energy storage and transportation electrification. Just to see the market for electric vehicle for battery would be huge, between 160 to 2 billions, if you can see around 2030. You can see market is divided in 3: watt-hours for portable use application, electronic application; kilowatt-hours mainly for buses and also vehicles, and also for home use. And then you can see megawatt-hours mainly for energy storage and so on. And you can see the electric vehicles is very, very high. Why here is small? Because energy density is increasing, so watt-hours we can be a little bit about 7 billions to 10 billions. So this is only battery. I'm not speaking about motors, or I'm speaking about electric vehicles. So what we developed the chemistry, so thanks to John Goodenough, who has invented lithium cobalt oxide, spinel oxide, and also nickel oxide and manganese oxide. So we are taking this original technology that first was introduced by Sony in 1991, and was changing the cathode, anode, and so on. We come from hard carbon to natural graphite, silicon natural graphite, LTO, and this is iron phosphate both, and this, as I said, since 1995. So why LFP? LFP are safe compared to other materials. Why we focus only in LFP, and you can see during my presentations. So only LFP, they can give the number of cycles like that. We charge and discharge at 100% SOC and DOD. And you can see over 15,000 cycles. If you charge at 60 degrees C, we have 7,700, even at 45. So it's a huge number of cycles, and this is also, you have the safety and the cheapest because iron is cheap materials. If we compare here, energy storage, this is Estonian was joint venture between Hydro-Quebec and Sony. Compared to NMC in market, you can see only when you change the cathode, you can see because it is nanoparticles here. So we can charge it fast, like 1C, and also you can discharge fast. And then for LFP, no need any cooling because are safe materials. I like just to show some cell using for energy storage here. So this is what you call it null penetration. This is triangle of fire. It's not material, is not safe because it's triangle of fire because the oxygen, the short circuit combined from the null penetration and oxygen coming from cathode materials. So if we show here, this is another module. This is, we call it barbecue test. So solid state battery is very, very safe because we have no flammable electrolyte at all. So in order to work the high specific energy, it will be very difficult to use lithium iron phosphate. It can be maybe with cobalt phosphate, but cobalt we know when coming in these questions, but we need to go to NMC or NCM. And NCM is the best solution for solid state battery or other new cathode material. We are not difficult to get 400 to 500 when we optimize NMC with the solid state batteries. So there was some propaganda about natural sources and so on, but I believe the natural sources, if you are making recycling and so on, is not so difficult. So you can see in Quebec here, we have a huge reserves on nickel, copper, iron, lithium, cobalt, manganese, and phosphate. So this is very another. So our government and Hydro-Quebec, we are working very hard how to promote these materials to respect of humans and environmentals and so on. So if you come to the next generations of solid state battery using NMC here, so we was using NMC 11, NMC 8 also based on rich nickel and so on. You can see the voltage profile, this versus iron phosphate here, and with different composition on NMC. And you can see the cycle of NMC with this new solid polymer electrolyte, it works, and we have today 250 cycle. In order to commercialize, the technology must be around 1,000 cycle. This is the requirement. So we are not making this is in coin cell batteries. We are making this is in large format batteries. You can see this is only Hydro-Quebec in the world that can make this kind of format. This is around 70 centimeters length. Because you know when you have no electrolyte, you're going to have the flexibility to use this battery for electric vehicle, buses, or also I said trucks and so on. So we come from 4 lab cells, 1 ampere hour cells, 30 ampere hour cells. These formats are very known. This one is using maybe at Nissan or GM. This one is using at iPad, iPhones, but this format is really new, and also we can have a very, very flexible shape also. As I explained before, what we are doing in Hydro-Quebec for 25 years is the circular green economy. We come with the raw materials, we make transformation here. For example, lithium, we go from ingot, alloying, extrusions, lamination, solid state battery, and we recycle. Because our electricity is very cheap, so we are not burning, we are using hydro metallurgy, because this is electrochemical methods, very easy to recycle. And then the people many are interested in our lithiums. We today, honestly speaking, we are only one company in the world that we are only to process in kilometers and kilometers thin lithium with protection of passivation layers. And then we can, so this is all what we can do with the lithium metals, 25 to 50 micron easily. And then the width, maximum width is 145 today. But as I said, we can process it to 1.5 kilometers to 1.5. Our experience today, we saw a lot of publication and so on, because we start working on lithium metal in 1979. So lithium-less, of course, for the lab and student is okay, but for us as company is not practical. It's very difficult because we need a lot of pressures and we need a lot of, I said, uniformity of the density of current by centimeter square and so on. So just this is some message also. For fundamental, yes, of course, we have freedom, but for application, it's difficult. So I finish my conclusion where, so I can see as we introduce the safest technology in the world for energy storage and buses. Today is using anywhere in the world. So for also from housing, also to the grid for solars and also for wind, especially in China, mainly using buses and energy storage and so on. We already come with the Gen 1 technology that today is commercially valuable by Bolloré Group. And we are coming with Gen 2 and Gen 3, and we believe that we hope, because Hydro-Québec is supporting us, and we hope that we come with a Gen 3 around 500 watt-hour and so on. So I am here as ambassadors, but people are making hard work. So sorry, but I am here, but this is teamwork and also open innovations. And usually my message always is collaboration, give a fruit, and we don't like just to close the windows and sit in our labs. So thanks to all our teams here, and thanks also to my collaborators. And I will hope that they get some questions and respond to you.